Okay, let's start. Do you have any questions? All right, so last time we started chapter 3, conditional distribution. So to remind you, the point here, right, is that we have two random variables, x and y, okay? Now, in 477, you would discuss the notion of the joint distribution, right, of x and y. And so, for example, if x and y are both discrete, then you would look at something like this, okay? So this is the joint distribution function. If both are continuous, then you will look at something like this. This is the joint density. Okay. And you could have, in 477, look at something like the conditional distribution of x given y goes to little y. All right. And for now, let's just focus on the case when both are discrete. And then we'll leave this case to be addressed a little bit later on. So here, let's say if both discrete, then, so first of all, right, basically, we are just looking at something like this. Probability x equals to little x given y equals to little y, right? Which by definition will be the joint divided by probability y equals to little y, okay? Now, on the other hand, what we should note is that this by itself, right, when x changes, or probability x equals to some value, given a particular value y, is a probability. All right. In other words, if you sum over all values of x here, then this is equal to 1, right? Well, it's clearly non-negative. And then if you sum over basically these joint sets of values of x, then you get this joint, you get this corresponding sum over the corresponding disjoint values over x here, right? So it is a probability. So in other words, right, we can, so this right here, right, this right here is referred to as the conditional distribution. of x, right, given y equals to y. Now, as you will see, because it's just basically, right, it is a probability, and it gives it assigned probability to different values of x. It's really also a random variable. Okay, so basically this is a conditional distribution, let's say, of a certain random variable. Okay, corresponding to some random variable. So you will see statements like x given y equals to y is a Poisson so and so, right? So for example, we will say something like x given y equals to y is a, let's say, a Poisson, let's say, I don't know, lambda times y, right? I'm just giving an example that may or may not be true, or something like that. So basically, it is a distribution. And so there are models, right, with that kind of distribution. So we will say it's a conditional, well, it's going to be a Poisson distribution, for example, a binomial distribution, etc. Well, not only that, right, it will also have, well, being a distribution, it will also have things like expectation and variances, right? We can also talk about expectation of x given y equals to y, and we talked about it last time. It basically just follows the same rule as expectation, but using this, okay, as our probability instead of the original probability x equals to little x. In other words, this is just it's just little x times probability x equals little x given y equals little y, right? Summing over values of x. Well, it also has conditional variances. Okay. And then here, right, it's defined as expectation of x squared condition y equals to little y, subtract, right, expectation of x given y equals to y squared. Well, and what is this? Well, it follows the same formula, but only with x squared. And then this is this sum squared. All right. Anyway, and there's more. The whole point is just a distribution, so we can just say whatever we want, right? With it, we can say as much as we want with the conditional distribution as with unconditional distribution, right? As with a random variable. So our task for this chapter, right, is to be able to study, okay, different examples of x, y, and look at, the conditional distribution of x given y, and then at least, at the beginning, to study what they are. For example, is it a Poisson, is it a binomial, y, etc., right? And the formula we will follow at the beginning, at least, we'll just start from the definition. What else do I want to say before we do some examples? Yeah, one last thing I want to say is like this. Eventually, we will move to this notation. Okay. Sorry. The conditional distribution of x given y. So basically, we will omit even this particular value, as you will see. The reason is because we want, after we kind of consider this for all values of y, then we want to look at y itself as a random variable, okay? This is a subtle step, but it's way more advanced. But as you'll see, at least from some point of view, it's natural. The reason is because in the abstract, at least, when we say condition on a value of little y like this, well, which value, right? Our formula works for all values of little y. So we might as well just not mention it, and we say this is true for all particular value of y, of the random variable y. Same thing here. Instead of saying that x given y equals to little y is a Poisson lambda y, we can say x given big Y is a Poisson lambda big Y, as long as we understand what that means, okay? Again, this move is very, very important because it allows us to, well, so of course, right here, the corresponding notation will be expectation of x given y, big Y, or variance of x given big Y, okay? But the big difference is that, for example, while this is a number, is a constant, this is a random variable, this is a random variable, opening up, things like we can take an expectation of a conditional expectation like this, okay? And one of the very, very big theme for this chapter is to say that this is just expectation, all right? So the theme, one of the theme of this chapter is computing, right, expectation by conditioning. And this is called the double, expectation formula or whatever you want to call it. But basically, right, this concept or this tool or this theme is only available because we move from, okay, instead of viewing conditioning on a particular value of y into y being a general value, right? Y being a random variable. All right. So those are the kind of like at least the basic things that we'll do at the beginning of the chapter, right? We'll try to understand at first how to work with this expression. Of course, there's nothing new about this, but now we attach it to a random variable and try to identify that random variable. And then, look at expectation and variances, and then move to, y being a general random variable instead of just a particular value. Okay. Any question before we begin doing examples? Okay, so let's see. So let x1 and x2 be independent binomials N1p and N2p. Okay. They want you to calculate the conditional distribution of x1 condition on x1 plus x2 equals to m. Okay. Any idea, any suggestion on what the result should be or could be? So the general theme of these kind of problems is that you would start out, at least if you have no idea what's going on, is you will start out with the definition. But, okay, you will always have this kind of answer in mind as the goal. So even though you do calculation alone won't be enough here. You will need to, or at least want to be able to identify what the conditional distribution is in terms of some familiar example, right? Some familiar random variable. So in this case, right, what are we doing? Well, okay, maybe let's ask the simple question. What is the support of this random variable? What values can it take? So x1 being a binomial, x2 being binomial, meaning they're all non-negative, right, and integers, then if x1 plus x2 equals to m, and we know that, that's what we condition on, then clearly, right, x1 cannot take a value bigger than m, right? So in other words, the value of x1, which is, right, the support of this, right, condition on the fact that you know the sum, right, x1 plus x2 equals to m, is that the smallest value is 0, right? But the largest value is what? M, right? If m is less than n1. But if m is bigger than n1, then the value is at most n1. So the minimum of m and n1. Do we understand? That's what kind of value x1 can take, conditioned on x1 plus x2 equals to m. Right. The reason is when we write down, for example, k, right, given this, that's what we're calculating, right? Then we know, or we must keep in mind that k is among these values only. All right, k cannot be beyond m because that's what the sum is. K cannot be beyond n1 because that's what x1 can be at most. Okay. Anyway, right? So for k equals 0, 1, etc. All right. So now once we identify that, then we just do the calculation, right? Okay. Now, how do we deal with this? How do we write this down? Well, the top would be equivalent to this, right? And again, you see the importance of k being less than m, because if not, m minus k won't make sense as a possible value of x2. Okay? So like that. And then what is this? Well, this is just a joint, right, of x1 and x2, and we know they're independent. So therefore, the top will be n1 choose k, p to the k, 1 minus p to the n1 minus k, and then m minus k, sorry, n2 choose m minus k, p to the m minus k. I'm running out of space here. Let me see. So n1 choose k, p to the k, p to the n1 minus k, and then n2 choose m minus k, p to the m minus k, 1 minus p to the n2 minus m minus k. Okay. What about the denominator? What can we do with this? So to work out the denominator, right, we need to know the distribution of x1 plus x2. If x1 and x2 are independent binomials with the same success probability, then what's the distribution of the sum? Well, sum will be a binomial with the number of trials being the sum, right, of the individual number of trials. And so here we have n1 plus n2 choose m, p to the m, 1 minus p to n minus m, n1 plus n2 minus m. Okay, so that's the calculation so far. And notice, right, let's say it's a pretty routine calculation, but you need to be able to, well, you know, use the joint of x1, x2, as well as recognize how the sum interact. Of course, I mean, there are many things you can condition on, but notice how this material is built upon chapter 2. So in other words, if your knowledge of random variable is not very fluent, then it's probably not going to be easy for you to work out this calculation. Okay. Anyway, so what do we do with this? So note, right, p to a k, p to m minus k, that's p to m. 1 minus p and 1 minus k, n2 minus m minus k is n2 minus m plus k, that's n1 plus n2 minus m. So they cancel, leaving us with n1 choose k, n2 choose m minus k, over n1 plus n2 choose m. Again, right, for what value of k? Values of k is 0, so k equals to 0, 1, etc. Minimum of n1 and m. Any question? All right. That's not enough. As I said, that's just kind of, let's say, a good start. So we've answered, let's say, this calculation by simplifying it, by working it out to a recognizable expression. And we still have to recognize it. In other words, right, we have to be able to make this kind of statement. So what is it? If probability of x1 equals to k, given x1 plus x2 equals to m, is this expression, what is it? Then x1 given x1 plus x2 equals to m is what kind of random variable? What random variable has this distribution? So it's the hypergeometric, right? Well, how many parameters do we need for the hypergeometric distribution? More importantly, right, what does the hypergeometric distribution model? So the hypergeometric talks about selecting, right, a sample in an urn with so many balls in one group, let's say blue, and so many balls on the other, which is red, right? And that's N1, N2 here. N1, N2 play the roles of the number, right, of members of each individual group. What else? For the hypergeometric, we need to decide how many balls are we, what's the sample size? How many balls are we withdrawing without replacement, okay, from this urn? And that's what M is here, right? That's what M is here. M is the sample size that we're withdrawing, okay, from the urn. And if you check, that's exactly what this expression is. Okay. Now, can we give an interpretation for this? Why is it that when x1, x2 are independent binomials with the same success rate, then condition on the total number of x1 and x2 plus x2, then it's going to be a hypergeometric like this. What's the interpretation? So it goes as follows, right? Basically, again, it's actually this picture too. You have two groups to experiment. One group, right, with N1 trials, one group with N2 trials. That's what X1, X2 stands for. On the other hand, right, you know that you want to select M total successes, right? So M here is the total number of successes. You want to, you want to select M successes from this total number of trials. Okay, so out of N1 plus N2 trials, you want to select M successes. So clearly, right, the way you do it is, and notice, right, this is where the same success rate comes from, same P. If these are different success rates, then you cannot do this calculation, but it's the same success rate. That's why you would choose K successes from the first group trials, and then the remaining M minus K successes from the N2 group of trials. All right. And when you do that, that's exactly how you would also operate with a hypergeometric random variable. Any question? So again, right, this statement right here and the intuition I just told you about, it's not just like kind of for fun or like kind of idle discussion. The reason is later on when and if we encounter this scenario, we will cut through this calculation and we'll simply say that this is the result. Of course, unless it's the exam where you are asked to explicitly derive this. If that's the goal, then yes, this calculation is necessary, okay? Because that's what the question is being asked right now, for example. But eventually, we don't have time to repeat all this calculation. We will simply say that we know, or we remember, or we recognize using our intuition, however you want to do it, that the conditional distribution of x1 on x1 plus x2 is a hypergeometric with the corresponding rate, with the corresponding parameters. Okay. The reason, right, is because, again, you have to cut through a lot of calculations here. That's the point of like thinking probabilistically. If you do every single calculation that's necessary, then you will get lost in a jungle of calculations and you will never get out. For example, right, the question here will be similar. Let x1, x2 be independent binomials. But now I ask you to calculate the conditional expectation. Okay. This should be quick, actually. What's the answer? The answer is, right, because we have worked out that this is a hypogeometric so and so, the answer will be whatever we know about the expectation of hypogeometric, which is m times n1 over n1 plus n2. Are we okay? Any question?
Sorry, where did we get this?
From the chart. From the chart where we remember when we walked through chapter 2, I asked you to list out all the basic models of discrete random variables, their distribution function, their support, their mean and their variances. And I said you must, you should, whatever, memorize these. That's where they come from. We can work out this expression for the hypogeometric per se, but like that's another problem that requires some calculation. Basically, I'm trying to say that some of this invokes memorization of how the random variable works, basically. Like for example, right, later on, let's say we have a Poisson lambda, and then if we look at this, then we'll just simply say it's lambda. Well, from where, who cares? Memorization, etc. Right? Yeah. So short answer is memorization. Long answer, well, falls into separate material, etc. But yeah, we need to know this actually. All right. Any other question? All right. So that's, of course, right. Let's suppose that the question is this. I'm not going to pose this question, but suppose this is the question. Now, what do you do? You would look up, right, the variance of a hypergeometric random variable. And whatever those numbers are, you plug in for the corresponding case here, for the corresponding parameters. Well, the reason I'm not going to ask this and the reason we're not going to figure it out is because if you look up the hypergeometric, the mean is very easy to remember. The variance is something that is, okay, why is the mean easy to remember? The mean is easy to remember because it has meaning, right? M being the sample size you pull out of the urn, N1 over N1 plus N2 is exactly the ratio of blue over, right, blue plus red. So you're just kind of multiplying the sample size with the success rate to get whatever, right, expected number of blue in your subsample outside M. So again, we're kind of like addressing that sort of previous question where do we know this? We know it from memorization, but not all memorizations are equal. You should memorize things that make sense, and the things that sort of don't make sense, it depends, right? I mean, by don't make sense, I mean there's not really a recognizable pattern to it, like the variance here. Okay, then those, if you work with it more often, then you memorize them. If not, then it's harder to memorize. Which, by the way, also goes like this. If it's something I leave as a question mark, let's say right now, you're not going to be responsible for it on the exam, let's say, right? Because I don't memorize it myself. But at least the things that I would consider routine like this, then, either you commit it to your formula sheet, that's fine. Or, right, you're expected to know this on the exam, for example. So this is expected of you. This won't be, for example. But anyway, right, the theme overall is you just kind of look up the hypergeometric and use your knowledge of the hypergeometric to feel this out. Any question? Now, so we have addressed this step, and this step, right? And even this step, we just didn't write down what the answer is. And then, right, let's talk about the moving to remove, right? Removing the particular value we're conditioning on. So for example, right, here, if we remove M, right, how will it look like? If we remove M, then what we're saying is x1 condition on x1 plus x2, like that, is a hypergeometric with these following parameters. Okay. So first of all, right, at some level, it's just a replacement of symbol with symbol. But it's much, much more than that. For example, right, in some way, this is a, well, I mean, I guess in Bayesian statistics, let's say, this, I'm not sure what's it called, probably a mixed distribution or something. But Bayesian statistics, right, is famous to have parameters being random variables, right? And that's exactly what we're having here. We have a distribution with parameter being random variable. But that's legal. That's perfectly fine. Why? Because we are conditioning on it. So when we condition on something, we acknowledge or we accept or we expect, whatever you want to use, that this is given. We just don't spell it out, right? Like that. On the other hand, like I said again, right, this is very much a random variable. So this is very much like a random variable. So it should be handled with care. And that's, the later sections in this chapter. But for example, one consequence is when we look at conditional expectation, again, dropping the particular value of M, then this will be x1 plus x2 times this. All right. And as you will see, right, that now this will become a random variable. Okay, this will become a random variable. This is a number. Okay, it's very important that I even spread out. This is a number, meaning it's a constant, meaning it's not random. This is a random variable. Why? Because x1 plus x2 is a random variable. Reason, for example, is if you take expectation of this, well, not much going on because you just get a number, right? Expectation of a number is a number. On the other hand, you can take expectation of this and it's a much, much more interesting object. Okay, so it's actually the topic of a later section, but I'll just want to demonstrate to you right now. So I'll ask you to do this, right? Calculate expectation of this in the above example. Okay, what's the answer? Well, the inner expression, right, is this. So and then of course, right, this being a random variable, what kind of random variable is it? Well, x1 being a binomial, right, n1p, therefore it's going to be n1p, right? Similarly for x2. But the p can factor out, right? So the final answer is that. But it's not just a answer, it's a number. What do we know of this? What is this? This is expectation of x1. Okay. Demonstrating that principle right here that I was talking. Of course, this is a much, much more general principle, but this is a demonstration of a particular case of how that works. Now, of course, no one will calculate, right, expectation of a binomial this way. There's no need, we just calculate directly. But at least this shows you that this works in principle and how, right, the different layers, the inner layer of the expectation, the conditional expectation, which becomes a random variable, and then how, right, the outer layer, which is this, will operate on what is being conditioned on to give you a number. Again, very, very sophisticated stuff. So, make sure you kind of see all these layers and how they work, right, to move forward. Any question? All right, let's continue. At x and y being independent, you know what? Let's call it x1, x2 as well. Horizontal. Okay, like that. Sorry, the textbook gives you a value. Doesn't matter, as you will see, right? Eventually we will remove the value. But for now, if you're not used to this thinking, and having a value there as a placeholder might help. Right? Did anyone work out what that is? So again, right, we start with the definition. Well, actually, we start with what? We start with the support, right? What is the support of this random variable? What values can it take? Well, again, right, the Poisson takes any values from 0, 1, etc., but all the way to infinity. So they take on non-negative value. So therefore, if the sum is something like m, x1 cannot be more than that. That's clear. So, right, m. But is there any other upper bound for x1? The answer is no, right? Because the Poisson itself has no upper bound. So unlike the previous case, where x1 itself is also upper bounded, right, by n1. Here, there's no such thing. So x1 can take any value from 0 to m, okay? In other words, right, for k being value from 0, 1 up to m, whatever one of these values are, then probability of x1 equals to k, condition on that. Oh, we just work it out, right? As before. Okay. And then exactly the same technique. And then using the fact that they're independent to give us the product, right? E to minus lambda 1 to the k factorial, e to minus lambda 2 to the m minus k over m minus k factorial, right? That's the numerator. What about the denominator? How do we deal with this? If x1 and x2 are independent Poissons, what is the sum of x1 plus x2? Well, it's also a Poisson, right? With rate being the sum of the rates. So x1 plus x2 being Poisson, lambda 1 plus lambda 2, right? So therefore, the denominator will be e to minus lambda 1 plus lambda 2, lambda 1 plus lambda 2 raised to the m over m factorial. Okay. Any question? And so, again, right, that's the first sort of step here, right? That the calculation. Next one is to be able to say what that is. And so, what can we say about this? So first thing we notice, right, is that the exponentials cancel. The second is that the factorials, right, lined up together like this. M factorial over K factorial, M minus K factorial. And then, right, you have lambda 1, and then M, right? The way we write M is M minus K plus K. Or as mundane as that is, this is lambda 1 over lambda 1 plus lambda 2 raised to a K, and lambda 2 over lambda 1 plus lambda 2 raised to the M minus K. Again, right, for what values of K? K runs from 0, 1 up to M. Or the final touch, right, is, what is this? That clearly is M choose K, right? So can we say the distribution of x1 condition on x1 plus x2 equals to M? Is a binomial, right? With how many number of trials? M trials. With what kind of success rate? Was P? This is your P. All right. So that's the step 2. We have interpreted it as a random variable. Any question? Well, of course, right, it goes without saying that you should notice this number because lambda 1 and lambda 2 are positive, right? That this number is a number between 0 and 1. So it fits, right, the choice for a probability. Well, the next one is not required, but as you'll see, right, a big theme of, well, let's say any field, right? A theme is you gotta memorize the basic knowledge, the core knowledge. Because if you don't memorize the core knowledge, then you're not gonna be able to operate using this, core knowledge to do any other work. For example, right, this eventually will be filed along this, the things that we memorize. Again, it's not that hard to work through this. Okay, in fact, I can, do this in 2 minutes. As you see, it just gets in the way of thinking. So eventually we're just gonna move, right? If we are given this, then this will be a binomial so and so. Okay. Again, unless the question is explicitly about deriving the conditional distribution, and we need to do the calculation. But anyway, right, on the theme of serving or helping with memorization, what is the intuition, or what's one possible intuition to say that this, yeah, it's reasonable to say that the conditional distribution is a binomial? Anything we can say about that? Well, the answer, right, is about understanding the meaning of a Poisson random variable. Well, what does Poisson random variable model? It models, right, the number of arrivals, right, or the incoming stream, right, of certain kind of events, right? Event can be as mundane as customer arriving at a store. Okay, so if you keep with that theme, then you can think of x1, x2 tracking the number of arrivals of, let's say, two types of customers to a store, male or female, if you will. Okay, the independent, well, clearly, I mean, I guess the male customers have no influence, right, over the female customers in terms of arriving at a store. And so if that's the case, then what is x1 condition x1 plus x2? Well, it's like if you know the total number of customers arriving at a store, you try to shift out, or you try to work out the number of males among them, right? Or I mean, if you want a more abstract description, if you know the total number of arrivals, you try to work out the number of arrivals in a particular category. Let's say category number 1. All right. And when you think about that, it's kind of at least intuitively clear that among M arrivals, that the number of arrivals belonging to the first category, it's got to depend on how the rates of arrival, right? Lambda 1 and lambda 2 are the rates of arrival. That the average number of arrivals per unit of time. And for example, right, the higher the lambdas, the more arrivals in a unit of time. So for example, if this is 1,000,000 to 1, then clearly, right, condition on a certain number, you would expect most of them to be from first category, because there are just so many arrivals, right, of the first type. So in general, it makes sense that the success rate, right, which is just basically how likely it is that a particular arrival is being of the first type rather than a second type, is a ratio, right, of the average arrival rate of that category over the total number of rates. So that's, again, right, I mean, it's a story, right? It's believable, but and it helps with memorization. It really helps with memorization, but rigorously, then we just have to do the calculation, right, to see how it works. All right, any question? The next thing we do is we remove, right, the conditioning. Again, it's a formal step, but it's important. So x1 condition on x1 plus x2 will be what? A binomial x1 plus x2, lambda 1 over lambda 1 plus lambda 2. Okay, like that. Why so? Because now we can write down, right? Oh, maybe I have an asterisk, right? So the next thing, once we know the conditional distribution, is we can work out the conditional, this is quiz 5, right? Yeah. Find the conditional expectation. And I will drop the equal to m. Because as I said, right, that's what we're moving toward anyway. And so might as well skip it. But here, let's also write down the conditional variance. Okay. So this step should be quick. The reason is, you have identified, right, what the distribution is, and then you just kind of work on your knowledge of the random variables. So what is this? What's the conditional expectation? Well, the answer is binomial, right? NP expectation is n times p. What about the conditional variance? Conditional variance is, well, binomial NP, right? Then variance is n p 1 minus p. Okay, so that's the conditional variance. Again, notice how quick the calculation is. I mean, it's not even a calculation, right? It's just working off your memory. If you know what this is. Of course, if you don't know what this is, then forget, right, answering this. So again, it's just kind of re-emphasizing how important it is that we recognize and we memorize these patterns. It's no more than that. At least in some cases, it's about memorization. Any question? All right. Next question. Again, kind of giving you a sneak review, I guess, a sneak peek of preview, right, of what's going on, what's going next. Compute expectation of expectation. And the second one will be a sort of a mouthful for now, but you'll see that is routine when we get to it. All right. What is the first answer? Well, what do you expect to be here? Well, if you remember the theme, right, the double expectation should return back to you expectation of whatever that you're taking off. So that's x1. And what is that? X1 being a Poisson lambda 1. So however the calculation comes out, should be lambda 1. Okay, that's what we expect to happen. Well, is it? Let's see, right? The inner expression is that. And then, of course, right, now again, notice that this is a random variable, so we can take expectation off. And clearly, right, this is lambda 1, this is lambda 2, expectation off, right? So therefore, we get lambda 1 plus lambda 2, giving us with the final answer as lambda 1. All right, any question? Now, what about this? So first thing to note, right, with this funky expression is that notice that at some level, conditional expectation and conditional variance are just random variables, all right? They're random variables in terms of what you are conditioning on, right? They're random variables being built out of what you condition on. But anyway, being random variables, then you can talk about their expectation and their variances, right? This is a variance of conditional expectation. Again, as strange as it sounds, if you look at the nature of whatever this object is, then taking its variance is a very routine procedure, if you will. So therefore, again, it's important that we understand each object that we're operating on before we even start operating on those. But once you understand that this is nothing, let's say, earth-shattering, then what is this? Well, this is that, right? So the first expression, and let me skip repeating steps here because, it's just basically a lot of symbols to write down. If you take expectation of this and you bring expectation inside, and that being lambda 1 plus lambda 2, right? Then the first expression will become lambda 1, lambda 2 product over lambda 1 plus lambda 2, right? That's the first expression. Okay. What about the second expression? The second expression is variance of this, which is that. Now, if you apply the variance operator on here, what happens? Well, you have to be careful, right? So far, we used linearity of expectation. So there's a constant here, but it doesn't affect anything because a constant just comes out of expectation. But with variance, right, the story is different. With variance of a constant times something is that constant squared, right? Times the variance of whatever random variable we're looking at. Okay. And the variance of this, right, being independent random variables, variance of the sum is just a sum of variance. So that's just that. Okay. So again, here we need to pay attention to the fact that there's a constant here which comes out as a square. Anyway, right, what is that? That reduces to lambda 1 times lambda 2 plus lambda 1 squared over lambda 1 plus lambda 2. Well, what is it? You see, this is the same denominator. So if we combine, we factor out lambda 1, we will get lambda 1 times over, which is lambda 1. Well, surprise, maybe not. But what is lambda 1 here? So notice that lambda 1 in the upper calculation plays a role of expectation of x1. Here, this lambda 1 actually plays a role of the variance. All right, the Poisson has that kind of property, right? That its expectation is equal to its variance. Okay, so there you go. So this calculation, right, which is this one, gives us that, which is an example of, right, the conditional variance formula, which says that variance of a random variable is expectation of the conditional variance plus the variance of the conditional expectation. Which again, right, is a much more sophisticated formula than this. But we will work with both and we'll use both to solve problems. But it's just giving you a preview of what's, coming up next. Any question? All right. So that's sort of like one aspect of things where, let's say that these are nice cases, okay? Nice case in what sense? Nice in the sense that we can say what the conditional distribution is. Now, I did say, right, that's sort of one of the tasks, but I don't want to kind of give you the impression that that's always to be expected. Meaning that sometimes when we do this calculation, okay, and we get the expression, it's just not one of those recognizable random variable. And that's perfectly understandable. Why? Because, the examples we have are just what? 5 at most, 5 or 6 out of right, infinitely many random variables we can write down. So it's not to be expected that every single case we calculate conditional distribution of is a recognizable random variable. But on the other hand, right, as two examples show, it's very important to be able to recognize the case when you can recognize, because then, right, all the tools you know about the binomial or the hypergeometric applies. You do not want to, in the middle of the exam, recalculate what these are and then apply the binomial or whatever, or worse yet, I don't know, apply a definition, right, of the expectation to this calculation, because that's exactly the case where you can never get out of, right? The calculation is just so complex. But what I'm trying to say is, right, I'm gonna give you the next example where it's not any of those recognizable pattern. We just have to work with, right, whatever we are given. But so it's both. Sometimes it's recognizable, sometimes it's not. It's our task, right, to distinguish which case is which. So this is quiz 7. Says there are n components. On a rainy day, component I will function with probability pi. On a non-rainy day, component I will function with probability qi. Okay. I goes from 1 to n. It will rain tomorrow. With probability alpha. Calculate the conditional expectation of the number of, well, you know what? Let's use the textbook language. Conditional expected number of components that function tomorrow. Number of working components. Well, no components that function tomorrow. Given that it rains. All right. What's the answer here? So first thing, right, is to just write down, I guess, the language, right, of what's given in terms of, let's say, symbolic, right, symbols. So, well, we have n components, and let's just say, right, and clearly we're looking at something like an indicator function, right? Let xi be 1 if component I works, 0 otherwise, right? And then there's something like a R random variable, right? That looks at if it rains, 0 if not, right? Okay. And what are we looking at? Component I will function with probability pi. So probability xi equals to 1, right? Given that r equals to 1 is pi. Probability that xi is 1 given r equal to 0 is qi, right? Okay. Well, it will rain tomorrow with probability alpha. So probability r equals to 1 is equal to alpha. What are we being asked for? We are asked for a conditional expectation of number of components that function tomorrow. Oh, what is that in symbols? The number of working components, right? Clearly, it's just the sum of xi, right? That's a number of working components. Condition that it rains tomorrow. So that's what is being asked. Okay. Now, what is this? So one thing I'm sort of maybe have said indirectly and not directly is what I said, that conditioning, right? The rule works as the unconditional case because conditional distribution is a distribution. It then implies, right, that the following, sorry, this is in general, that if you have a linear combination of conditional expectation, then what happens? It also comes out like this. All right. So basically, conditional expectation is linear, just like expectation. So, right, which again, I mean, I did not say it directly, but it's sort of implied, right, by saying that conditional distribution works like distribution. Therefore, what is this? Well, it is sum of expectation of xi given r equals to 1, right, by linearity. But what is this? Well, xi being an indicator function, right? Condition on another random variable will change its distribution, but will not change the value it takes. Because if it takes value 1 or 0, condition on something else will not change the value it takes. In other words, it still takes value 1 or 0. Oh, I mean, well, okay. Let me say that it does. It may change, but in this case, right, I hope it's clear that, right, being how it's related to component I working in the rain, it should not change. In other words, what I'm trying to say is condition r equals to 1, xi still takes value 1 or 0. But either it works or doesn't work when it rains. In other words, this is just Bernoulli, even in the conditioning. In other words, this is just expectation, right, will be success probability. It works just like the Bernoulli, conditioning or not. Therefore, it's just sum of pi. And that's your answer. Any question? So the thing to note here is what? The thing to note here is that this information is redundant, at least for this question. Of course, it's not redundant in general if you have to work with this model, right? But at least for this question, it's not used, okay? Not used anywhere. So again, right, emphasizing the importance of being able to understand what the problem is asking for. Is it asking for a conditional expectation or is it asking for an unconditional expectation? If it asks for an unconditional expectation here, we will need, all right, the probability that it rains tomorrow. Second of all, right, that sort of like just highlights the fact that conditioning is like the regular distribution. Conditional expectation is linear, just like the regular expectation is linear. I guess, thirdly, if you will, I don't think this falls under any model, right? This is just a problem. I mean, sorry, it doesn't fall under any known random variable. Being known being the ones that we talked about in, last week or in probability, right? In 477. This is just a model. So this kind of goes along what I say, where sometimes when we do conditioning, we just have to work with what's in the problem, right? It's not something that's kind of given. Well, having said that, it's like a Bernoulli, right? I was using the Bernoulli kind of variable. So anyway, right, it's a combination of all those things. Any question? All right, let's continue. So this is question number 2 in chapter 3. It says that x1 and x2 be independent geometric P. So they're both geometric P, okay? But they're independent. Find the conditional distribution of, again, right, you guess what it is. X1 condition on x1 plus x2. Again, I will drop the equal to m. We can fill it in when we do the calculation, but eventually, right, dropping the m is going to be the language we'll be using. Also, this problem has a flavor of guess. The textbook asks that, right? Guess, but guess being the intuition I was referring to. So it's both, right? You try to guess first and then verify with calculation, or if you prefer, calculate first and then justify with intuition. Doesn't matter. All right, any guess? Guess doesn't have to be right from the start, but as long as you can have an intuition to back up your guess, that's good. And again, guesses, if you make it more often and with well-informed reasonings, it will help strengthening your intuition, which is actually very useful, or I would say even essential, right, for a course like this. Any guesses? First of all, right, what does x1 plus x2 represent here? If x1 and x2 are geometric, what is the distribution of x1 plus x2? And what does it represent? X1 plus x2 is a negative binomial, right? What am I saying? It's not n1 plus n2. Negative binomial 2p, right? What does this 2 represent? 2 is the number of trials until the first 2 successes. Okay. So again, right? I just set the interpretation right there as well. This represents the number of trials until the first 2 successes. All right, so let's take a look. So you have so many trials, right? And you have the first success, and then let's say so many trials, and then the second success, right? But what you're having now is you have the total number is conditioned, so you know it. You know the total number of trials until you get 2 successes. You know this. And you want to know that given that number, let's say 10, right? It takes 10 trials to get 2 successes, first 2 successes. And what are you asking? You're asking for the number of trials to get the first success. What does that look like? If it takes 10 trials to get to the first 2 successes, what's going to be the number of trials to get to the first number of success? No guess? All right, so let's see if the calculation helps. So again, right, what do? We do probability x1 equals to k, condition x1 plus x2 equals to m. What kind of values k can take? K can take any value from 1 right? No zero, because we need at least one trial, right, before the first success. And then K can take up to M, right? Well, okay. M what? M minus 1, right? Why? Because x2, right, will also take at most one value, right? So at least one, right? So that's what the most x1 can be is M minus 1. So what is it? Well, again, right? I'm just gonna take a shortcut here. X1 equals to K, X2 equals to M minus K, right? That's the joint on the top divided by probability that X1 plus X2 equals to M. Well, then, right, these are being independent geometrics. They are 1 minus P to the K minus 1, right? Times P, and then 1 minus P to the M minus K minus 1, right, times P. Okay? Divided by what? Divided by, this is the negative binomial. So what was it? Among the previous M minus 1, right, position, choose one position to be your success, right, your first success. The remaining ones can be failure, right? And how many failures do we have? We have M minus 2 failures, right? And P square success. P square for the 2 successes. Okay, any question? So when all said and done, right, what do we have? All this number cancel, leaving us with 1 over M minus 1. Which is what? Which is a uniform distribution, right? A discrete uniform. So in other words, this is telling us that condition on the total number of trials to get 2 successes, the position or the number of trials to get to the first success can be any number from 1 to M minus 1, right, to the one before this. Is that okay? So that's a uniform. If you want, discrete uniform. Any question? All right. Let's do one more. Yeah. So, course 9. This is question number 5 in chapter 3. It says an urn contains 3 whites, 6 reds, and 5 blacks. 6 of these balls are randomly selected from the urn. So it's a sample of size 6. So you let X and Y, two random variables here, denote the number of whites and blacks selected in the sample. All right. So the urn has so many balls, right? So many colors. 6 are selected, and you count, right, among the 6, how many are white and how many are black. So that's sort of like hypergeometric, right? But just with more categories. So this is like hypergeometric with more categories. So you keep track of first category and let's say the second category right here. So they ask compute the conditional probability mass function, or that's a fancy word for say conditional distribution, right? Of X given Y equals to 3. Also compute expectation of X given Y equals to 1. So this is like a hypergeometric, right? But you're conditioning on the number of types, the number of subtypes, right, in the sample you select. All right, so what is it? So first of all, right, when Y equals to 3, what can X be? What values can X take? X being number of white selected, right? It can be anywhere from 0 to, well, first of all, right, you can select more whites than whatever that's there in the urn. So 3 is the upper bound according to this. But of course, if the 6 balls total selected and then 3 of them is black, then no more than 3 can be whites, right? So it's so coincidence, but the 3 and the 3 are the same, right? 6 minus 3 is also 3. But technically speaking, it should be the minimum of this and 6 minus that, right? Anyway, 3, right? Okay. But what is it? Well, so just goes with the definition. Okay. So first of all, are these independent? Like the previous ones we worked on? Are X and Y independent? Answer is no, right? This is unlike, so we've worked with conditioning before where somehow whatever x and y we end up having, right, they're independent. Of course, we didn't condition on y before, right? We conditioned on x plus y, whatever. But x and y, we in the previous ones we worked on are independent. Here it's not. So you cannot split into this product, okay? If you split, it's wrong. Reason, of course, is that if x is like big, then y has to be small, right? If you select a lot of blacks, of course, the number of reds should be less because there are only 6 balls totally selected, okay? Anyway, so the point here is you just can work by counting, right? So in your sample, there's k whites. So of course, right, by counting, you do what? 14, right? Choose 6 as a numerator, right? And then out of 3 whites, you choose k whites. And then out of 5 blacks, you choose 3 blacks. And then the remaining reds, you choose the remaining, right? 6 minus k minus 3, okay? That's reds, right? So white, blacks, reds. What about denominator? Denominator is still over 14 to 6, right? But here you only have to do 3 blacks, right? So 5 choose 3. What about the other ones? Well, the other ones, you just kind of pick the remaining 3, right? From the other group. Who cares how you pick it, right? Because here we don't care for the composition of whites and reds. So that's 9 choose 3. Okay, so far? Any question? So again, right, when it checks out, what is it? This cancel, leaving us with 3 choose k, 6 choose, so 6 minus k minus 3 is 3 minus k, right? Over 9 choose 3. Do we recognize this? This is a hypergeometric again, right? So it's pretty simple. I did say, right, this is like a hypergeometric with 3 categories. But if you condition on the number of one of the categories, then it's sort of like, you know, reduce it to two categories, right? Sort of like intuitive like that. So this is a hypergeometric with what? 3 from the first category, 6 on the second categories, right? And then you're choosing a sample of size 3 out of it. Okay, any question? So what's 3 and what's 6? Right, 3 is the number of blacks. 6 is the number of the remaining ones, right? What about that 3? That 3 comes from where? That 3 comes from 6 minus 3, which is the, yeah, number of balls non-black in your sample, okay? Okay. So then the textbook asks you to compute expectation of x given 1. X given y equals to 1. How do we do this? Well, the answer is right. You're not going to be able to do it by definition. You will have to do it by recognition. So of course, right, they could have done y equals to 3. They do y equals to 1 to see if you understand what's going on. The point is, right, before you do this calculation, you should recognize that x given y equals to 1, right, is what kind of distribution? It will still be hypergeometric, right? With what? 1, and then 6, and then 5. Right? Because this 3 is a number of y that you condition on. 6 is the 6 ball selected. This 3 is 6 minus 3. Is that okay? So therefore, expectation of x given y equals to 1 will be 5 times 1 over 6, which is 5 over 6. Which makes sense, right? In a sample of 6 balls, if you have 1 black, you expect 5 or 6 whites. Any question? All right, if not, then let's stop here today. If you have questions, I'll answer. If not, I'll see you on Wednesday.